Chapter 1, Section 8, Exponential Notation and Order of Operations. We're going to talk about what exponential notation means, order of operations. We're going to simplify and how that distributive property ties into that again, and the opposite of a sum, which we're going to lot of errors around here where this subtraction deal, that's why I keep talking about that negative of or additive inverse of or opposite of is the same as taking negative 1 times it. All mean the same thing. Well, we're going to talk about what this exponent thing is. And exponents are kind of like are to multiplication like multiplication is to an addition. When we have exponential notation, we have a base, which in this case is 3, and the 4, the exponent, means that the 3, the base, is a factor, part of a multiplication, in this case 4 factors, or 4 times. So, 3 to the 4th power is not 12, it's really 3 times 3 times 3 times 3, which is 81. And we read this as 3 to the 4th power, or simply 3 to the 4th. The number 4 is called an exponent, again here, and 3 is the base. And we end up with these things here. Now they talk about some nicknames of exponents. When we say things are squared, if you think about how we have to express area, we say, well, we got a two-dimensional surface. We need to have a two-dimensional object that we can put together and say it's this many squares, right? So, and the area of a square is side times side. Like if this was a 2 by 2 square, it would be 4 units in the square. Well, because we use that so much for area, which comes in squares, the nickname for to the 2 power is squared. So we could say A area is equal to side squared, or side to the 2 power is the formula for area of a square. Well, with volume, which we use a lot, if you have three-dimensional volume or spaces, right? To have a volume, we have to have cubes. So we have a cube has the same length side, and depth. So to get the volume of this cube, you take s to the 3 power, or thus the nickname for it, which is s cubed. So you're going to do things like write this multiplication in exponential notation. The base is 10. It is a factor 5 times, so it's 10 to the 5th power. And then you're going to write these exponents, or these powers, as multiplications and simplified into the actual calculation of that. So when we have 5 to the 2 power, that really means 5 times 5, or 25. Now negative 5, the quantity taken to the 3rd power really means negative 5 times negative 5 times negative 5. And you'll end up with a negative. If you count your negatives, that shortcut is I have an odd number of negatives. I'm going to end up with a negative result, and it'll be negative 125. And they talk about, here's that associative law of multiplication again, is we can change the grouping. In other words, they group the first two together, which is a positive 25 is the product of negative 5 times negative 5, those two factors. Same thing if we have the quantity 2n to the 3rd power, that's 2n times 2n times 2n. We can change the order, which is a commutative property, and we can group them differently by saying, hey, let's group these 2 times 2 times 2 and n times n times n, and you'd end up with 8n to the 3rd power. So they're going to talk about a couple of things here. One is to look for patterns. As we look at like this base 7 to an exponent of 4, which is 7 times 7 times 7 times 7 is 7 to the 4th power. Well, here's 7 to the 3rd power. Here's 7 to the 2 power. What would this 7 to the 1 power be? Would actually just be 7. And if I continued on too, what do you think 7 to the 0 power would be? And we'll come back to that, but we'll talk about that later. So the number of factors decreases by 1 each time. To extend the pattern, we say 7 is the same as 7 to the 1 power. In other words, 7 is a factor once, which kind of makes sense when you think about what that actually means. So here is the algebraic way for the definition of exponential notation. For any natural number, now natural numbers are the counting numbers, which are 1, 2, 3, 4, 5, and so on. So it has to stay in that set of natural numbers, and that's what they're saying n represents. So in other words, these exponents have to be positive and non-zero. So it could be 1, 2, and so on. They say, well, it just means that b, the base, is a factor of this multiplication. Remember, factors are parts of a multiplication, and you'll count them number of times it's multiplied, and that'll equal your exponent n. Now, order of operations we're going to cover again because we haven't had exponential stuff yet. And where does that fit in that PEMDAS, or the mnemonic to talk about order of operations? And they kind of introduce maybe some other brackets we're not so used to using, like the rounded brackets, square brackets. Here's the set notation brackets, as probably we've seen before. Absolute value symbols are also grouping, and fraction bars are actually a grouping thing, which is easy to miss. So if we have this multiplication, 4 plus 2 times 5, order of operation tells us we have to do what's in the grouping symbol first, which is 6. And we get 6 here. And then we multiply times 5 to get 30. Now, here's that exact same order with a different grouping and a completely different result. Here I'd have to do what's in the grouping symbol and take 2 times 5, which is 10, and then add 4 plus 10, and I get 14. So it definitely makes a difference about grouping symbols and where you put those, because these are mixed operations, where if it was all addition or all multiplication, it wouldn't matter. The associative property works. But not necessarily so when you have mixed operations, so you got to be careful. So here's the rules for order of operations. You simplify if possible within the innermost grouping symbols. Here's some examples of that. You have the rounded brackets, square brackets, this set brackets is what I call those, and absolute value bars, and above or below fraction bars. We simplify all exponential expressions, perform all multiplication, division left to right, perform all addition and subtractions working from left to right. So they're going to mix some stuff in here. We got to make sure that you understand how to use order of operations, which I don't think should be pretty much review. But when we get exponents in here, it's easy to kind of not follow order of operations. In this case, for example A, 3 times 4 is all to the 2 power, and this one is 3 times 4 to the 2 power. Well, order of operation means I have to take 3 times 4, which is 12, and then square it, or take it to the 2 power. 12 times 12 is 144. Where this one is a completely different result. I have to square the 4 first. Order of operations, I have no grouping symbols, so I do exponents and then multiply. 3 times 16, I get 48. And that's really what that example is showing, is that you cannot assume that these two things are the same. Now this really comes into play when we're talking about negatives. When we have a negative x squared, it may help to write this as a negative 1 times x squared. And that's why I talk about this all the time, where you remember when we change from subtraction to addition, they say you add its opposite. So if you have 5 minus a negative 3, you add the opposite of negative 3. Well, the opposite of 3 is the same as the additive inverse of 3. So I could say to change from subtraction to addition, I could say is add its additive inverse. Well, multiplying by a negative 1 does exactly the same thing as taking the opposite of it or the additive inverse of it. So I could say to change from subtraction, again, I could say is you add the negative 1 times it. Well, this becomes very important when we get these types of expressions. And it seems kind of, like, why do I have to make it so complicated when I talk about 3 different ways? Well, opposites, negatives, all that kind of stuff are big deals. We got to make sure we get our signs correct, and this is one of the places where there's a lot of errors. Well, we look at this and we say negative x squared. According to our order of operations, we tend to think that this negative is part of that variable, but really it means negative. This negative means the opposite of x squared, or the additive inverse of x squared, or the more useful way is to say this means negative 1 times x squared. Now I use order of operation, which is whatever I put in for x, I need to square that and then take it times negative 1. So in this case we have, and they want to evaluate x equals 5 for this expression, which is negative x, the quantity, to the 2 power. And b is negative x to the 2 power. Well, in a, I'd substitute in 5 for the x, and I get negative 5 to the 2 power, which is negative 5 times negative 5, which is a positive 25. This one, I put in, and think about that this really means negative 1 times x squared. So then I take negative 1 times 5, substitute it in for x squared, which means I square the 5. According to order operations, I need to square the 5 before I do multiplication, and I get negative 1 times 25 is a negative 25. Big difference, and that's what they're showing us, that there is definitely a difference between those two expressions. And in this case, we have a grouping symbol to a power. Well, we'd still do what's in the grouping symbol first, then we'd have to follow order of operations. And remember, the other mistake I see a lot of times is we think multiplication comes before division, but division and multiplication are in the same level of order, so you just go left to right. So we'd go negative 15 divided by 3, which is negative 5 times 8, which is 40. It'd be a whole different answer if you said it's negative 15 divided by 24. That's another real common error that happens. So make sure you follow order of operations with these exponents. So they're showing us more and more complicated expressions here where I'd have to follow order of operations. This is definitely, if you're not doing an algorithmic style to your problem solving, when you run into this stuff, you're making a big mistake. This is a time to practice this. When they go from here to here, that's fine, I guess. But I would write down the original. And actually, when I write down originals, I try to get rid of subtractions because they're problematic. I also would probably want to get rid of division, but let's leave that alone for now. And why would I want to do that is because I can't use the commutative and associative properties on subtraction and division. But here's the original, and then the next line down I would write this. I do what's in the innermost bracketing or grouping symbols, and I get 3 minus 5, which is negative 2. Now I'm inside this grouping symbol. I rewrite everything except the calculation I'm going to do, which is I have addition, multiplication, and exponents here in this square brackets. Well, order of operations, I need to do the exponents first. So now I have this new expression. I still have a grouping symbol here. I do multiplication before I do addition, so I get 9 plus negative 16, which is, that addition is negative 7. So now I have this expression, 8 divided by 4 plus 3 times negative 7. Well, I can go left to right with the division and multiplication. 8 divided by 4 is 2, plus, right here, this 3 times negative 7, which is negative 21. And then I add those, I get negative 19. Now, especially in my math labs, when you're working on this stuff, you put in here, and let's say I make a math error somewhere in here, and I get negative 42 or some other number, and it says wrong. Now, rather than starting all over, I would prefer to say, what did I do wrong? If you write out your work this way, and plus think about what and why you can go from one step to the other. That's how you study for this stuff, is how do I really get firm on order of operations? Well, as you practice this, think about this. This is doing the innermost bracketing first, right, to get that negative 2 here. And then I do exponents because that comes before multiplication and so on. Actually think about why and how it works step by step. And you're practicing a way to study the terminology. So use the right terminology when you do this. Now remember what they talked about. Fraction bars basically are grouping symbols. So I can treat this numerator here, this big numerator, as a grouping symbol around it. And then I go to the innermost and do that. And then I can say this is a grouping symbol here too. And they basically rewrite it as a division. I'd probably leave it as a fraction, but they're showing us so that you can really see the order of operations. So, but they do too, leave it as a fraction, right? So they do this part here as a grouping symbol. I do the exponents, I get 16. 3 to the 2 power is 9. They did the innermost grouping, which is 9 minus 7 is 2. That's all they did for this step, right? So now I have this new fraction, and then I do order of operations again. These are grouping symbols for the numerator and denominator. So I do the multiplications here, which is end up be 24 plus 20, and 16 plus 9 is in this grouping symbol for the denominator, and I end up with 44 over 25. Now simplifying in the distributive law, sometimes we cannot simplify within grouping symbols, so we're going to use this as a strategy to be able to simplify this expression. So let's look at this one. And again, if you don't understand these properties or these laws really well, it's pretty hard to get real strategic with it. But the idea is that I still want to think about where I'm going with this. I have x's here, and it would be nice if I could group those together and actually add those like terms. So we're going to have to do a couple things first. In this case, we distribute. When we get these variables in here, there's a lot of things go away, like I'm stuck right here, right? According to order of operations, I have to go to the innermost grouping symbol. And I kind of like this in here in this way when we run into variables, because now in here I got 4 times x plus 5. Well, according to order of operations, I have to do the multiplication before I can do addition. So I'm done. I can't do anything else with this unless I have some laws that can override order of operations. So we get strategic and figure out a way to be a problem solver by applying these laws. And I need to know kind of where I'm going to do this, or decide when to do this, rather than some memorized technique. You're going to run into a lot of problems just saying, oh, I got these set of multiplications, this is how you do this, or this set of exponents, this is how you do this, and you just repeat that and not think about what is going on here with your basic stuff, order of operations, associative, distributive, commutative laws, and then problem solving strategy, right? So in this case, we're going to make a decision. Not necessarily saying it always has to happen this way, but if they want me to simplify this expression, usually I'm going to try to get to something that has like terms where I can use the distributive property again to create an addition. I can do, but I need to get some things out of the way here. Well, one way is, well, I can distribute this according to the distributive law and go 2 times 4x plus 2 times 5, and that's what they're showing here. So they can rewrite this expression as 5x minus 9 plus 8x plus 10. Now I have all addition, really, and I change this. If I asked you for the terms of this expression right here, the terms would be 5x, negative 9, 8x, and 10. They always express terms in addition, so why not change it to an addition? Because I really can't change the order or use the associative or the commutative property as an order or the associative property to group things unless it's addition. We tend to just, in the book does this, they say, well, this is really plus negative 9. Well, I would write it that way. I'd go 5x plus negative 9 plus 8x plus 10. Now I can say, hey, it's addition. I can change this to any order I want. I can go 5x plus 8x and negative 9 plus 10. Well, then I can group them together and use the distributive property to say, hey, I can factor out the common variable here of x and say that this is 5 plus 8 times the quantity times x, or 13x. Negative 9 plus 10 is 1. So we use distributive, which then sets up maybe the possibility of combining like terms. But also notice they're not writing down all these steps anymore about changing order and grouping together differently. You know, the assumption is that you should be pretty comfortable with basically skipping the explanation for doing that. Well, here's another one where we distribute first and then look for opportunities to combine like terms. So, one more step, one more use of really the same things we've covered before to be able to problem solve, or in this case they want us to simplify expressions. Well, now this opposite thing comes in here. Again, this is why I really emphasize that the opposite of, additive inverse of, are the same as negative 1 times it. So in this expression here, it says when we have the negative of the quantity x plus y, it indicates that it's the opposite or additive inverse of the sum of x plus y. When the sum within the grouping symbols is preceded by a negative symbol, we can multiply the sum by negative 1 and use the distributive law. In this manner, we can find equivalent expressions for opposite of a sum. Or I would say the opposite means, again, or additive inverse of means negative 1 times it. So when we see a negative of a parentheses, you should put in there negative 1 times whatever's inside, which sets up this property of negative 1, means that I can distribute that, and I'd end up with a negative 1 times each term in that addition, and I'd end up with negative 3x plus negative 2y plus negative 4. And I would leave it that way rather than convert to subtraction. So it is easier to enter this into my math labs. But the book on tests and everything else, if you left this as negative 3x plus negative 2y plus negative 4, you would get that correct. And I like that process because if I need to go on and use this expression like in an equation, I still may need to do some commutative property and associative property, and I would rather that it be still expressed in addition. So they explain this with algebraic definition. It says for all real numbers a and b, the negative of the quantity a plus b, or another way to say that, the opposite of the sum of a and b, is equal to the negative of a plus the negative of b, or negative a minus b. And I would say the opposite of means negative 1 times it, which means then you use the distributive law, and you probably don't even need to use this as a new property or some boxed in thing, right? So they go through this process of saying, well, how do I deal with this type of thing that happens? And it comes in the form of subtraction too. So when I change this subtraction, 3x minus the sum of 4x plus 2, well, I can rewrite this as this negative, or changing from subtraction means take the opposite of and change it to an addition, right? Or add the opposite of, or add the additive inverse of, or add the negative 1 times this, right? Well, that's what they do. They say, well, we're going to go plus the negative of that, right? That's changing it to an addition. And then distribute the negative 1 times that, and we end up with this new addition, which we then can simplify because I have like terms, and I get 3x plus negative 4x. Group those together, that's 3 plus negative 4 all times x, or negative 1x, which is negative x, right? That's the rule that they gave us about this negative 1 property, right? So the proper form would be not negative 1x minus 2 or negative 1x plus negative 2. It would be better to say negative x plus negative 2. All those things really mean the same. So they're getting into more complex subtractions here. So I would change everything to an addition rather than decide that, hey, I'm just going to change this part to an addition. I would change everything to an addition. Make sure you distribute the negative 1 over this quantity right here. So the negative 4t squared goes to positive. The positive 9t goes to a negative 9t. I'd leave it as addition again and do that. I know the book does it differently all the time, and you'll see that. You need to get comfortable with seeing that. But I think it's just good problem solving skill to stay in addition when you can. So here's a couple more examples. They go through just about every different way it can occur. Remember, you still got order of operations issues, and that's the next part of this. Like I said, we're just talking about expressions and simplifying and stuff like that. Well, next chapter we're going to start putting an equal sign in, and we're going to end up with solving an equation. Okay? Which is a good reason to stay in addition, is that you may need to use that to apply your commutative or associative properties later too. So that's the end of chapter 1. We've got quizzes coming up and chapter tests. Good luck with that. Get prepared and show me what you know.